So the third talk is given today by John Shawe, which is a professor at UCL, where he directs the Center for Computational Statistics and Machine Learning. And he's also the head of Department of Computer Science. His research has contributed to a number of fields ranging from graph theory through cryptography to statistical learning and its application. However, his main contributions have been in the development of the analysis and subsequent algorithmic definition of principal machine learning algorithms founded in statistical learning theory. He has co-authored 2 very influential textbooks on kernel methods and support vector machine. He has also been instrumental in coordinating a series of influential European networks of excellence, culminating in the Pascal network. And so today, John is going to speak about conditional mean embeddings for reinforcement learning.
Thank you very much. Thank you for the invitation. It's a great pleasure to be here. It's really nice. So I think I'm in the similar bubble to Niccolo here. This is really a talk that is looking towards a situation where applications can be made in reinforcement learning that are really beginning to make an influence. And the question is, how do you manage with small amounts of data? And I'm going to also go with Niccolo in not talking about deep learning. And so this is looking at a situation where you're trying to learn with relatively small amounts of data, and therefore deep learning may not be the method of choice. Of course, the enormous progress made by DeepMind in terms of applying reinforcement learning to Go was able to leverage large amounts of data because the rules of the game are so well, they're determined, so they can do self-play and so on. So there is a large amount of data there. But in real-world applications, note the worst, real world, of reinforcement learning, that may not always be the case. So anyway, this is the motivation, and this is joint work with Guy Lever, who is now actually at DeepMind, and Ronnie Stafford. I think I wanted to set the context by saying that I think kernel methods have been an excellent compromise between flexibility and principled regularization. Clearly, the deep learning has shown that their regularization is too steep or too sort of restricted in some way. It's not allowing the flexibility that deep learning networks or neural networks afford. And that is something that, if you have large amounts of data, means that it may not be the method of choice. But in limited and controlled, where perhaps data is limited, this may still be a very excellent choice. And there have been many extensions that make them usable in unusual applications. And for reinforcement learning, we're going to look at this conditional mean embedding approach and show how it can be applied. But there's going to be, in order to make it practical, the need to introduce sparsity in 2 aspects. And so this is really, if you like, this is the real-world stage, as it were. Okay, so I'm just going to give a quick introduction to kernel methods, because I'll need to introduce the way of looking at things in order to motivate this conditional mean embedding stuff. So I'll then talk about that. I'll then... you're right about the delay here. It does take a while, doesn't it? Yeah. Okay. The reinforcement learning to show how the conditional mean embedding is sort of works with the reinforcement learning as a modeling tool, and then the sparsity ideas and show some empirical results. Okay, so kernel methods are based on this idea of working in a high-dimensional space implicitly through this kernel function. So the kernel function is a sort of shortcut to computing the embedding of the input. So x is some input and z is an input. Phi is some embedding function that puts it into a high-dimensional feature space. And rather than explicitly compute that, we can compute the effect of doing that on 2 inputs and taking the inner product in that space directly with this kernel function. So that's the trick, and it has this property that the kernel matrices must be positive semi-definite, which follows from the fact that this is actually computes the norm squared of some vector in that feature space. Okay, so these two properties are the ones that are required that make a kernel function a valid kernel. It must be symmetric, and that property that I just showed you here, that all kernel matrices must be positive semi-definite. So it means that we can then define kernels on virtually any object, provided that these properties are satisfied. So we can do it on discrete objects and graphs and networks and so on, and many developments have taken place in that direction. And then, provided we can map standard linear algorithms to use just inner products, and this is typically done by representing the sort of learned weight vector as a linear combination of the training data, then, and of course it will require two-norm regularization, so there are restrictions, but provided you take those restrictions on board, you can map many algorithms into a sort of kernel version or kernelize them, and obviously ridge regression, PCA, CCA, SVMs, and so on. Okay, so what I wanted to do quickly was to show you how a sort of outline, if you like, but of the proof of how that construction is formed. In other words, given a kernel matrix that has that positive semi-definite property, how do you actually create this feature space that corresponds to the inner product? And the reason I'm doing that is not just to cause you pain, it's to try and motivate how the application to the conditional mean embedding occurs. So the way this is typically done is to create a feature space that's composed of functions. So it's slightly strange, sort of counterintuitive. Rather than creating points, we actually create, the points are actually functions in this space. And they're functions that are linear combinations of the kernel with one of the arguments fixed to an input point, and the function is the function formed by putting in an argument, the second argument, into the kernel function. And we take finite combinations of these with real valued weightings, and these xi's are any choice of input points from our input space. So X is our input space. And then we define the inner product between two such functions by defining it between two basis functions, which are just kx dot and kz dot. And the inner product between those two functions is defined to be that, and we can extend it to functions of this type. And in fact, the embedding function is just the mapping that takes the input point to this particular function where the first argument is fixed to that input point. So with these definitions, that we actually can show, grind the handle, this is indeed a feature space, this is indeed a mapping, that the kernel on two input points corresponds to the inner product between the two mappings. You can sort of see that defined here. It can be extended to all functions of this type. And so this actually does the job for us. But the important point from what I want to talk about is that it actually has this nice so-called reproducing property, that if you take a function from this space and you take its inner product with the embedding mapping, the embedding of the point kx dot, then actually that is the value of that inner product is the evaluation of that function on that point. And you can sort of see that if you imagine taking this function and taking its inner product with kz dot, then essentially what happens is the z just gets replaced into that function, and so this is the evaluation of that function at the point z, or in this case the point x. So this is the so-called reproducing kernel Hilbert space, or the reproducing kernel property of this particular way of defining the feature space. So this is the thing we're going to be using in this conditional mean embedding trick. Okay, so what is a mean embedding? So if we think about probability distribution on the input space, then it defines a point which is the expected value of the mapping of the input under that distribution into the feature space. So it's just the expected value of that function. Now, if you think of this sort of as a complex sort of set of features, we can also think of it, it could possibly be taking the moments of that function, the square, the the cubes and so on. So think of it in those terms. It's a way of accumulating information about the distribution in some point in a space. And so this mean embedding is some way of representing that distribution in that feature space. And of course, you have an empirical counterpart from a finite sample, which is just the, the finite combination. Now, this, we might not be able to compute this, but in principle, because we may not be able to actually know what this feature mapping is, and it might be some complex or even infinite dimensional vector. But anyway, it certainly can be defined in that sense. Now, there's a sort of surprising property that despite there being no restriction on the dimensionality of f, if the probability distribution has support in the ball of radius r in the feature space, so what I mean by that is that the distribution on the input space maps to a restricted region in the feature space. So for example, if we were using a Gaussian kernel, this would be true with r equals 1, since all points have norm 1 in the feature space, again with a Gaussian kernel. Then you can actually, with high probability, bound the norm squared, or the norm difference, between this true mean and this empirical mean. And it's actually a 1 on root m with a log of 1 on delta. So if, as I said, with Gaussian kernel, this would be 1. So there's a nice sort of, estimation property that we have about these empirical embeddings relative to the true embedding of this distribution in the point mu p. So these are just 2 points in the feature space, mu p and mu hat. Okay, so they satisfy this property. So now, mean embeddings for expectations. So let's say we wanted to compute, this is where we're using the reproducing property, we wanted to compute the expectation of a function, which is something we will see we want to do, for under this distribution. So we want to compute the expectation of f of x. Now remember, f of x is actually, by the reproducing property, is just the inner product between f and phi of x. This is a linear function, so we can, and f is now fixed, so we can take the expectation inside, and so we actually can evaluate an expectation of the evaluation of a function by just taking the inner product of that function with this point, this mean embedding point of the distribution. And we can actually show that this is actually a good estimate. If we take an empirical version of it, we can get a reasonably good estimate of that evaluation by just looking at this difference between these inner products. Again, Cauchy-Schwarz tells us that this is bounded by the norm of the function and that previous bound that I had on the norm between the norm of the difference of these 2 points. So again, this shows us that we can actually use this way of estimating the mean embedding as a way of getting estimates of the expectations of functions, and this is uniform, if you like, over all of the functions with a particular bound on their norm. So we're actually able to use this as a sort of way of computing the expectations over a whole set of functions. Okay, so hopefully that's set the scene. Now the actual thing we're interested in is conditional mean embeddings, which is where we actually are interested in distributions that are conditional on some observations or values, y, so the probability of x given y. Now in that case, the distribution, and hence the mean embedding, is a function of y. So we actually think of this mu p of x given y as just a mapping from this values y into the feature space. So the mean embedding, you remember, is a point in the feature space. Now we're mapping a y to a point. So this actually sounds complicated, but now actually we're just really looking at regressors. So we're really looking at mappings from an input space or some observation space y to a Hilbert space. I mean, think of it as just a two-norm space. So this is just a multi-dimensional regressor. Okay. So now I'm going to, let's just set the scene so you can see, these tools from kernel methods, and particularly this mean embedding tools. Now, I'm now going to do a quick diversion to remind you about reinforcement learning. Apologies if you're familiar, which I'm sure many of you are, but I just wanted to set the notation and make the connections, and then you'll see how we can actually use these techniques that I've just described in the reinforcement learning context. So the idea of reinforcement learning is to model agents that learn through acting in an environment and receiving feedback from the environment in the form of a reward or punishment. So it's also known as sorry. Okay. Sometimes it doesn't actually connect. Okay. So it's also known as a Markov decision process. You have a set of states, you have a set of actions, and given that you're in state S and take action A, there's some sort of probability of transitioning to a new state, which is given by this P of S prime given S, comma A. There's a reward function, which is a bounded value between 0 and 1. I'm not sure where that bracket came from, but is a function of the current state and action, or could be just of the current state. I mean, you can vary the way these things work. And there's a discount. What you tend to do is discount future rewards in favor of rewards in the near time future, discounted by a factor gamma. And the task the agent has to solve is to decide a policy, in other words, a way of acting. So it's given the current state, it has to make a decision which can be a probability distribution over the set of actions, or it could be a fixed action, but it has to decide, given the state it's in, what action to take. So it's not a history, it's just the current state. Okay, so that's the task. And the agent might have experience where it's been in state S1, it's taken action A1, and then it's moved to state S2, and it takes action A2, and so on. And the idea is that it's the initial state is maybe from some initial distribution, and then the action that it takes is its policy action, selected according to that probability distribution, which is a function of the state, and the action is chosen, and then the next state is given by the transition probability given the current state and the action taken. And the expected return is the expected value of the reward that you might receive if you follow that policy over an infinite horizon. But obviously the horizon is effectively finite because of this exponential discounting of future reward. So this is what you're interested in optimizing, this reward. There's also a value function, which is the value of a state given that you're operating policy pi, which is basically the expected reward you will receive if you follow policy pi starting from state S. So this is the value function. And you can also add an action to that where you allow your first action from that state to not be chosen by pi. So you can actually choose an action A as your first action and then follow policy pi. And this gives you a sort of leverage to decide how to improve on your policy pi. So that's essentially you're interested in, typically you pump prime with some initial policy and then you iterate to improve your policy over time. So the v pi is this value function, satisfies the Bellman equation, which is the expected value of the action taken that policy now. So this is not choosing your policy, deterministically initially, but actually following policy pi from the start, the reward you get, and then the expected value under the S primed chosen according to that action of the value function. So this is sort of a, if you like, a recurrent equation. There's also the Bellman operator, which allows you to map a value function under this operator t pi, which it gives you the update by following the policy one step. The optimal policy, sorry about all these definitions, but again, it's just to set the scene. The optimal policy is the policy that gives you the best possible value function. And there's one policy that works for all states, so it's there is an optimal policy that will deliver the best value. And this can be computed, as I suggested, mentioned quickly before, by various techniques that involve taking some sort of policy in order to get yourself started, and then perhaps policy iteration, where you then update to a policy that's greedy, perhaps taking the best action at the next step in order to maximize this plus this expected value of your current policy, and that will give you an improvement, and you can iterate your policy in that way, or value iteration, which is just looking at the value function and choosing the policy that maximizes your current estimate of the value function, or by dynamic programming if you have a small finite set of states. Okay, so now I'm going to move to the connection with the previous sort of framework of kernel methods. And this is going to be made by assuming a linear form for the value function. So I'm going to choose a linear form, but in this kernel-defined feature space. So I'm thinking of, here's a state S mapped into some, more complex feature space, and I'm going to be representing my value function as a linear function in that feature space where the weight is indexed by the policy. Now, if you want to then solve the Bellman equation for that weight, you will have this sort of equation to solve. This is the value function of the state. I mean, I've just rewritten the Bellman equation in terms of using this. So this is the reward that I receive by following the action from that state, and this is the value function that I get once I've taken the step, the single step transition by taking from state S action pi of S. And this is where we can see now the potential of what we're wanting to compute here is an expectation, where we can see that the conditional mean embedding approach may be able to be used. So this is, exactly the kind of thing we want to do, is to compute the expectation of this function under this distribution, which is a conditional distribution, conditional on a state and an action. So we want to build a model of the dynamics that makes it possible to solve this. And as I suggested, the conditional mean embedding is a clean way of doing that, because we can then compute this very efficiently. Because this typically is one of the hardest, sort of most problematic things that you need to do. Okay, so let's go to see how we can use the conditional mean embedding in this situation. So we've got this linear function, which we're using to represent the value function, and we're interested in computing this expectation. So this is just going to be using the conditional mean approach. We take the expectation inside the inner product because it's a linear function, and now we have this conditional mean embedding point here that enables makes it possible to evaluate this expectation. So if we have this point, we're able to estimate this point, we are then able to estimate this this expectation. Okay, so we need a mapping from the state action pair into the feature space, which is the expected embedding of the state that I reach when I take action A in state S. So it's the expected value of this feature vector phi of S primed, where S primed is chosen according to that distribution. So how might we find that? Well, the way we approach this is to set up this loss function, which is we make a mu hat, which is an empirical estimate of this mu here, based on the training data, and we're assuming that we have a sequence of training experience, which is we were in state Si, we took action AI, and we ended up in state Si prime. And so this mu hat of Si AI is, if you like, the expected value, and this is the actual observation, and we try to just minimize the mean squared error of this, and this is just in the Hilbert space, so we're able to estimate, to compute that quantity. And this provides, if you like, the training criterion that we can use for learning this mapping mu hat, which is this estimate of this mapping that we're interested in, which is going to enable us to calculate these expectations. Sorry, how much time do I have? 20 minutes? Oh, okay. So the solution has this form. So it's a linear combination of the phi si hats, the mappings as you might expect, the feature space, the feature mapping corresponding to the states points that we arrived at, and these alpha i's are going to be computed effectively by a regression algorithm. Now, I'm going to sort of skip over that, but once we've got that, sorry, I should move back here. Once we've got that, then our expectation of the v of s primed is just given by this inner product, and that will actually be this sum here with the weighting now with this v of s I primed. So this just becomes an inner product between this vector of alphas and the v, which is the vector of values on the on these points si primed. So then the Bellman equation reduces just to a linear system on this vector v. V is equal to r plus gamma times av, where r is the sort of expected values of these rewards, and a is basically these ai's computed at the various observed states that we were in. So effectively, we've reduced the Bellman equation to a finite MDP. Now, there's just a finite set of points, which are the values at the sort of observed states. But it generalizes to a value function for all points in the input space. So it's actually, you know, the learning part becomes a finite MDP, but actually we're solving optimally for the information we have and under the assumptions we're making for this continuous MDP. So we sort of reduce a continuous MDP to a finite MDP, which is kind of nice. Unfortunately, the size of the MDP in most, you know, sort of as soon as you start to look at something practical, let alone real world, then this becomes, you know, too large a set of states to solve. So we need to introduce this sparsity idea to try and, you know, represent the information in a small set of states or a smaller set of states that will make these computations feasible. So there are two ways in which this is done. The first is to find a sort of a compression set of states that are good at representing the state space. And this is done in a greedy fashion. I think this could be possibly improved, but this seems to be quite an effective solution. You're basically trying, just greedily, you start with a few candidates, but then you greedily look at how well you can represent your new observed state as a linear combination of the earlier states with a one-norm regularization. And if it's bigger than some tolerance, delta the error, then you add your new state into your compression set. So it's just basically a very simple idea. And then for learning these coefficients, which I said these alphas are basically learned through a regression. I mean, you know, it's very sort of straightforward in a way, but this learning would be infeasible if we were to use all of these states. But by compressing here, we also still make, this would still be infeasible to solve, and we need to use a technique to reduce the complexity of this, and we turned to matching pursuit. So I just have a few slides about matching pursuit, which sort of motivate the theoretical analysis of that. So I'll skip very quickly over that, but basically it's just a greedy selection of training examples that determine directions in order to create a subspace that in the feature space that is well suited to the task that we're interested in solving, and then you deflate and you just add these, again, a greedy method, these sort of dimensions that are, but they're determined by the training examples. And that allows us to actually apply some generalization bounds based on the sparse reconstruction idea, which if you can reconstruct a function from a small subset of the training data, then you can actually make your generalization bounds go through. So the reason this might sound, well, surely that's not a problem anyway. The problem is if you start adapting your feature space based on your training data, then all of the standard bounds break down. So you need to have some way of sort of controlling or handling how you define the feature space, and the way we've done it, or matching pursuit does it, is in terms of a finite set of trained data. So you sort of exclude those guys. They are used to define the feature space, and then you use the rest of the examples to do your analysis in a normal fashion. So it's sort of, you have to do a sort of union bound over the possible choices of those. So I think I'll skip over that, but that's basically the idea there. It's, yeah, I think that's enough. So these slides are just taking you through that. This is the sort of the bound and the combination with and this is the algorithm that allows you to choose those directions effectively. And this is actually a plot that shows maybe there is some agreement between the bound and the performance in a sort of a CCA example. Okay, so that was just, if you like, a little detour into that analysis of matching pursuit. So this now is the sort of combined algorithm for this reinforcement learning using conditional mean embedding. So I mean, basically, it's just putting together the things that I've already explained, but you've got this way of generating the compression set. You're doing this through a number of iterations which improve the performance. So in each iteration, you're taking some experience, gaining some new experience based on an updated policy. You're then incorporating that experience into this compression set. If you need to sort of creating a compression set, you're then doing this basis pursuit, matching pursuit idea to create this set of things that will represent your regressor. You're then solving for your regressor here, and this is now a manageable size of problem because of these sparse reductions, even in quite interesting applications, which I'll show you in a minute. And then you basically do a policy evaluation, but because it's a finite MDP, you actually can just solve it by dynamic programming. So the actual solution of the policy is really very efficient. Efficient, I mean, modulo the size of the thing, but it's of the size of this finite MDP. So it's order, n cubed if n is the number of states. And then you do a greedy update of your policy, okay? So that's basically the idea. So here are some examples that show how it might operate. And this is, obviously a fairly simple benchmark problem of balancing a pole on a cart by applying a force. And the important thing is here that we're actually learning relative to a very small number of training iterations without any, we're not putting in any knowledge of the physics of the cart. It's sort of learning that as it goes. That's essentially what this conditional mean embedding is attempting to learn. Interestingly, this green line is the sort of, if you do it with the full, without doing this sparse reduction, but the red line is the compressed or the sparse version. But the sparse version, we actually did it to make it feasible, but actually performs better as well, which is a little, so I guess it's doing some regularization at the same time. So the important point, though, is that it's learning in really very small number of trials. Here's a slightly more complicated example of a quadrocopter, which has got a 13-dimensional state space, position, velocities, and some angles. And there's a 3-dimensional action space, so again, real valued, of desired velocity vectors. So it's not going down to the low level. The low level is controlled by a PID controller. So sort of this is more like at the sort of meta level of where we might go next and so on. And the task is to navigate to a point, or there's a holding pattern of staying, a number of copters staying in a circle. And here's, again, reasonably good performance in that, again, the compressed guy is doing better. And with a smallish number of training iterations, we're able to get, you know, a very good cumulative reward. So the RKHS controller seems to be better in high-dimensional state spaces. So it's you know, it is able to leverage somehow this, you know, give it a very flexible state space, but it somehow manages the complexity with this regularization effectively. You know, this will make Niccolo happy. Attempts to do this with deep learning have proven difficult from, you know, data sparsity. As I say, you know, this is actually small amounts of data. That's, I think, the point that's here. So it's not actually a deep learning, though, you know, we are also trying to use this kind of technique glued together with deep learning, with some success in cases where there's more data. So we're not against deep learning. Okay, so that's basically the take-home message. I think, you know, I think kernel methods do provide a flexible tool that incorporates regularization in a principal fashion. I think, you know, this idea of mean embedding, conditional mean embeddings are really interesting in that they can sort of allow you to compute expectations in quite interesting cases. And in this case, the application to reinforcement learning is a very kind of, you know, natural marriage in that that's what you need to compute within the Bellman operator. And it has this interesting effect of translating a continuous space problem into a finite MDP that you can then solve. But you need to do this, sparsity is crucial in making this work in anything like a real-world problem. So I'll finish there. Thanks.
Any question? Good.
Hi, nice talk.
Thank you.
I was wondering, so I assume with limited samples, the choice of the kernel may have some important impact on the performance. So would you have any theoretical or empirical insight about the role or the impact of the kernel?
That's undoubtedly true. We were actually fairly naive and used just a Gaussian, you know, simple kernel. But I think if you were able, I mean, one of the questions I wanted to follow up on was, you know, say you had some partial knowledge of the physics. Could you embed that into the kernel and still allow yourself to, you know, have the luxury of not knowing the physics exactly, but actually, how would that impact in terms of the learning rate? And I think that would be a really interesting experiment. Well, we haven't done it, but I think that's a, you know, that's where you might be able to incorporate partial knowledge. But I think, you know, in terms of, you know, the controllers that you sort of build in your knowledge and you assume it's exact can be quite brittle. Whereas this might give you a little bit of an edge in that you could say, okay, I've got some knowledge and I build it in, but I'm allowing myself the luxury of actually, you know, the physics isn't quite right, there's, you know, things that aren't measured correctly and so on. So yeah, I think that would be a really interesting question.
How sensitive are the results to the choice of the regularizer in the kernel? The variance in the Gaussian kernel. So.
I'm not sure about that, but we certainly had a kind of, you know, cross-validation, recalibration going on in various stages of the algorithm. So it certainly is sensitive, but I don't think very sensitive, but you do need to be careful in terms of, and that actually was one of the most computationally, as you might expect, difficult parts. Again, an online algorithm that could do that for you would be very welcome.
I got a really dumb question. We can see that the regularized version does better in terms of what the controller does. And I was wondering if you had any type of insight about what it meant on the model side, that is there some sort of sparsity issue that shows up in the model that allows this thing to actually do better with the regularization? Or is there some other insight that comes out of the fact that this regularization works well?
So I would say, you know, what can happen if you have too many points. I mean, think about it. Basically, probably the way to think of this is think of that helicopter traveling around. The points are sort of covering the trajectory, and they're kind of accumulating information from bits of the trajectory that are close to that point and averaging or sort of using that information. I guess if you have too fine a grid, then these points are kind of subject to the noise of maybe just one or two trajectories happening to go through that point at some point. Whereas if they're slightly sparser, then it's accumulating more, averaging more information from more trajectories. And that may be giving it a better chance. But again, you know, we don't have an understanding of controlling that or why that, you know, how you would set that. But, I mean, one thought I was hopeful we might be able to do is this idea of, you know, sort of hierarchical. So you might start with a very sparse and you get the idea of how you travel for this region, that region. And then if you want to get finer grained control within that region, you go to a sort of more fine. And you could even then decompose the problem so you actually only look in that region at the points. But we haven't been able to get that to work. So that's, you know, that's a hope, but it isn't a reality yet. But, thank you.
Is there any more question?
Sorry, another naive question is, does it exist, are you sure of the existence of a policy for which the value function is linear with respect to the kernel? Is it something straightforward? You assume that the value function was dot product.
Yeah. So, sorry, what's the question? Is that a reasonable assumption, or?
Yeah. Is there a policy which would have this particular form?
Yeah. I mean, Gaussian kernels are universal. I mean, I think that with the right kernel, yes. Yes, but clearly that's not an assumption that is going to be true, you know, that it will necessarily. I think, you know, if you say the regularization is making this trade-off between fit and so I think, you know, if you set, as Nicola says, if you take a universal kernel, then with a sufficiently large weight vector, yes, you can represent any policy. But clearly, you're actually going to be regularizing, and so you're not going to hit, you know, an exact policy. So it's all predicated on assuming that you get a sufficiently good policy. And I think, you know, the hope. I mean, what we're trying to sort of arrive at is the situation where, despite the high-dimensional space, you've sort of managed to get away with almost like a low-dimensional sort of representation of that policy. But the linear, you know, the low-dimensional choice of the low dimension is sort of taken with respect to the data. So you sort of are getting the best of both worlds is the hope. Yeah. Okay.
Farida, I also have a question. Are you interested in the robustness of your optimal strategy with respect to gamma, this discount factor? And because in stochastic game theory, we're looking at what happens when gamma goes to 1.
Yeah.
And we're aiming having not optimal strategy or policy, but almost optimal policy for any gamma big enough. Let's say bigger than 1 minus something very small. Do you look at this kind of results or properties or not at all?
No, we haven't. I mean, that's... so sorry, I didn't quite follow. You were saying you want a strategy that's robust for...
Yeah, which is robust with respect to the discount factor gamma.
Yeah.
You say, if gamma is big enough, bigger than 1 minus epsilon, then my policy is epsilon optimal or something similar, something like that.
Okay. Interesting. No, I haven't. I mean, I think we just took a reason. I mean, yeah. To be honest, I didn't do the experiments, of course, so I'm not exactly sure. But I think it was a reasonably large, but not. You know, we weren't optimizing somehow over lambda, maybe 0.99 or whatever it might be, and that was just used throughout. But it would be interesting to see if the policy you learn with some value, say 0.9, actually performs reasonably well with 0.99. This might be another way of bootstrapping to, you know, sort of in a hierarchical fashion. So you sort of do something that's reasonably good with, you know, a small set of states, with a sort of smaller gamma, and then take finite grids with a larger gamma as you sort of try to get a better policy. But it'll be interesting to see.
Any more question? No? Well, then we can take again, Sean.